Okay, we're going to start in on Chapter 7 and start in with electromagnetic radiation. Okay? Now, electromagnetic radiation is defined as a form of energy that acts as a wave as it travels. And it can travel anywhere, but it can also travel in space. Okay, it does not need a medium to travel through. This is going to include things like visible light, X-rays, ultraviolet, infrared light, microwaves, and radio waves. And it will travel at the speed of light in a vacuum at 3.0 times 10 to the 8th meters per second. Vacuum just means devoid of any other matter, not the appliance. So that's what that one's going to mean. And all forms are combined to form the electromagnetic spectrum. Now, we've seen this before in Chem 1. The electromagnetic spectrum. On one end you have gamma rays, you have, I want to go back again. You have gamma rays, you have X-rays, ultraviolet, your visible light. Notice the violet and blue end is towards the ultraviolet side. You get all the way to the longer wavelengths of red, infrared, microwaves, radio waves, FM being slightly shorter than AM. And remember, this is going to be your shortest wavelength. This is going to be your longest. Okay, and some of the other things we're going to talk about is frequency as well as energy. And shortest wavelengths are going to have the highest frequencies as well as the highest energies. And the longest wavelengths are going to have the lowest frequencies and the lowest energy. Okay, and if you think about that, that's why FM and AM radio waves are safe for us, because they have such low frequency and low energy. On the flip side, the gamma rays have such short wavelengths, they have very high frequency, have very high energy. That's why they can potentially do damage to our DNA because of that energy. Okay, then kind of back up a little bit, but if we define some of these things, wavelength is abbreviated by the Greek letter lambda. It's the distance between points on adjacent waves, and a lot of times it's described in nanometers. And just as a reminder, there are 10 to the 9th nanometers in 1 meter. Frequency is this lowercase v, it's the Greek letter nu. It's the number of waves that passes a point in a second, and the unit is 1 over s, or hertz. Sometimes you also will see it written as s to the negative first. And they're inversely proportional, which we just saw as one goes up, the other goes down. Or in other words, the waves with the really long wavelengths have much shorter, smaller frequencies because they're not passing as often, and the ones with the really the short wavelengths have very high frequencies. And we'll demonstrate that with the Slinky. Remind me if I forget. And then here's the equation where we have c is the speed of light, which we know, 3.0 times 10 to the 8th meters per second. We've got wavelength and we've got frequency. Apparently that's really important. Okay, now some math problems. Again, I just kind of defined what those things were. Practice problem number 1. If we have light that has a wavelength of 310 nanometers, what do we know? That the speed of light is equal to 3.0 times 10 to the 8th. It gave me my wavelength. I went ahead and I have to convert it to meters. The reason why is that these meters have to match up because they're going to cancel out. Okay, we want to know the frequency, so we write the equation. Okay, we plug and chug the numbers in. We end up with a frequency of 9.7 times 10 to the 14th hertz, and 2 significant figures in our data, 2 sig figs in our answers. Okay. Now, second practice problem, this is just the opposite. This time we want to know the wavelength. I put in meters, but that's kind of a given. And again, our frequency is 3.2 times 10 to the negative second hertz. We know our speed of light. We show the equation. We plug and chug. This time we end up with 9.4 times 10 to the 9th meters. Okay, that would be the wavelength of this particular type of electromagnetic radiation. Okay, and again, this is just showing you some different waves. Here's the wavelength that's defined by adjacent points on the wave. You can really use any points, but here you have a frequency of 8 hertz, 4 hertz, a frequency of 8 hertz, and a frequency of 16 hertz. And you can see as the frequency goes up, the wavelength goes down. So it's just again to demonstrate that they are inversely related. Okay, then we got to talk about the nature of matter, about as short as I can get it. Okay, now again, this should be a review from Chem 1, but before 1900, scientists thought that matter and energy were totally different. Okay, we thought of energy primarily as waves, we thought of matter as particles, and there was no way for those two worlds to collide or coexist. Alright, so again, we had matter that was particles, it had mass, we could identify where it was, that's what we mean by position. Energy, typically we thought of as a wave, we thought of it as massless and being delocalized, meaning that it does not have a position. That's all that means. Okay, localized means we can't identify where it is, or delocalized rather. Then along came a couple of experiments that changed that sense, and we all of a sudden had to update our theories. Now Max Planck, who if we hopefully remember, he at least has a big long number named after him, he said that an object actually emits energy in the form of small packets of energy called quantum. And this whole idea of packet was pretty revolutionary because as opposed to just this continuous amount, it actually was only a certain amount that could be present. And so a quantum is the minimum amount of energy that can be gained or lost by an atom. Okay, that's what we define a quantum as. And here we have our second equation, where delta E, don't worry, it's not that much thermo, it's going to be equal to Planck's constant times the frequency. And it's the same frequency that we saw in the last equation. Okay, same thing. And you're going to see how we tie those equations together here. Now, for Planck's constant, which you will get, I believe it's on the AP Chem sheet, but I'll show you, 6.626 times 10 to the negative 34th joules times seconds. So here's our second type of math problem, where we've got the energy equals Planck's constant times frequency. So if we had this time, bring all this stuff up here, whoops. Alright, the frequency of a gamma ray photon is 6.0 times 10 to the 22nd. We want to know the energy. Again, the other part that we know is Planck's constant. We've got our equation. We have our numbers plugged in chug, and what will happen here is that the second unit will end up canceling out. So when we do energy with these types of equations, the unit is also in joules. Okay, and remember, we just know how to go back and forth between kilojoules and joules and etc. So, but the energy is in joules, and that comes from Planck's constant because it's joules times seconds. Okay, Einstein came along in 1905 and added on to Planck's theory. Now remember, Planck's theory at that point was really the whole idea of quantas of energy, or quantum, which I think is really just the plural version. He suggested that electromagnetic radiation, including light, can also be viewed as a stream of particles, as opposed to just a wave. And what he came up with was called the dual nature of light theory. And dual means two. So really that we can treat light both like a wave as well as a particle. And you saw me do this last year, but if you think of it, it's, this would be our wave shape, but if you can also think of it as a stream of particles traveling like a wave, that's all Einstein was getting after, was that sometimes we have to look at light like a wave, sometimes we have to look at it like a particle, depending on what it is that we're looking at. Okay, so Einstein proposed that radiation itself is really a stream of particles called photons. Now remember, we don't have to understand all the background why information here, really just the end results. The energy of each photon, this is a little bit of accepting the proof here. Okay, this is just our energy equation. He also ties in the wavelength from our previous equation and the speed of light, just manipulating the equations. And he also showed that energy had mass. And so here is his famous equation. We don't have to do much math with it, but that energy is equal times mass times the speed of light squared. And that's what E equals mc squared is going to stand for. Okay, so then the next guy to come along who was pretty important here was de Broglie. And de Broglie came along in 1924. I'm kind of jumping around just a little bit, but we'll back up next unit to talk about the hydrogen line emission spectrum in Bohr's model. He was French. You don't have to pronounce it right. Well, probably would matter to him, but I won't mark you off. Okay, suggested that matter also has both particle-like and wave-like characteristics. So de Broglie flipped it around. He said, okay, if we can treat light like a particle and a wave, then why can't we do the same thing for matter when we need it to, when it doesn't make sense? And the de Broglie equation is a little bit different. We're not going to do a ton with it, but you should refer to page 296 of your textbook, and it will walk you through a sample practice problem. It's sample 7.3 of how we might see the de Broglie equation. Okay, we've seen the numbers. It's the letters rather. It's just a matter of plugging and chugging. Okay, and then the nature of matter. Here's definitely accept the proof here. And this is where he kind of tied it together, or where it came from. Here was our speed of light equation. Here was our just manipulating our speed of light equation. We've got our energy. So you see the arrows here. We combine those to get the de Broglie equation that we saw on the last slide. We've also got E equals mc squared. So we tie those two together. We rearrange it. And finally we end up with another equation that shows the relationship between, or de Broglie's equation that shows the relationship between the wavelengths, Planck's constant, our mass, and our velocity. So, excuse me, just some different things. And note on this that this is v for velocity, okay, and this one is the frequency. They're different letters, so don't get that too confused. So anyway, okay, big main take-home points. Shows that anything with both mass and velocity has a corresponding wavelength. So just a connection piece on that one. Big main ideas. Matter and energy are not distinct. They actually overlap. We can look at energy as a form of matter. And light, we can also look at energy as a form of matter. We can also look at matter as a stream of, it's kind of acting like a light. It's kind of acting like a wave. Now, there are some commonalities, is that larger objects typically behave mostly particle-like, okay, and where we're going to see where we can treat matter like a wave is really going to come in with electrons, and they're pretty small. So that's part of the reason that we do make this conclusion where we say larger objects are mostly particle-like, and that smaller objects are typically mostly wave-like. Okay, and that's where we're going to talk about this with electrons when we get into quantum theory. Okay, see you in the next video.